Thank you very much for the introduction. And uh, today, hi everyone, I'm Wenqi Huang, and today I'm very glad to be here to introduce our recent work for non-Cartesian cardiac MR imaging. We developed a new method called new implicit K-space for binning-free and single-shot MR reconstruction. And as we all know, MR imaging is a very useful technique, and also it's very complicated. And if we want to get the image, we need to acquire the data in the signal space, which is called K-space. If we acquire enough data in the K-space, and we can simply apply an inverse Fourier transform to get a very clean image. But in practice, there are some limitations about their MR physics, and also the limitation of their health condition of the scanned subject. And we can only get a limited number of K-space data with a limited time. That will cause a corrupted image, like on the right-hand side. And so that we need some reconstruction algorithm to make this image clean. Nowadays, existing MR reconstruction method in the deep learning era usually follow these ways. People usually input the undersampled K-space data and the initialized image from this unsampled data and put them into the network. The network can be arbitrary network, it can be physics driven, it can be an end-to-end like UNet, and it also can be transformers. And the network will output a predicted image, and we use a fully sampled image to calculate the loss and then supervise the training of the network. After training, we get a newly sampled undersampled K-space data, and the network will output the reconstruction directly. But there are some limitations of these methods. The first limitation is that this kind of deep learning methods usually need a large data sets. And it's very difficult for cardiac MRI because if we want to get fully sampled data, we usually require the scan subject to hold their breath. It can be even more challenging for patients with heart diseases. And the second limitation is a loss of temporal resolution. And to know that, we need to know how we got all of this sample K-space data. Along with ECG signal, we use a tiny golden angle continuous sampling strategy. And along with the ECG signal, we continuously sample a set of K-space spokes, K-space lines with the same time interval. And in the end, we map and sort all of these sample K-space lines into one average heartbeat. And for each sampled K-space line within this heartbeat, they have their own time stamp. But usually we cannot get an image from only one K-space line, so that we need to do the data binning. That means we need to grab some neighboring K-space lines to assume they are sampled at the same time point, like T1, and grab the next few lines for T2 and for T3, exactly. And in this way, we just construct the minimum operation unit. For example, here, the binned K-space is a minimum operation unit. In the following ways, we can do arbitrary things like we apply inverse non-uniform transform, a Fourier transform to it to get the image space, to get another frame to the image space, and combine them together to finally get the beating heart. But actually, these K-space lines are not sampled at the same time, but with the data binning, we usually assume they are happening at the same time. That will cause some loss of the temporal resolution. The third limitation is an imperfect image frequency mapping. If we take the minimum unit of the sampled point, that's like being k-space, several k-space lines. But these k-space lines are not on Cartesian grid. It's just have some arbitrary angles. That will cause a lot of trouble if we want to jump between this non-Cartesian grid and this Cartesian grid in the image space. So that we need some special things which called non-uniform FFT. But with the non-uniform FFT, we usually have the unavoidable interpolation error and non-trivial density composition field estimation. That will cause a lot of trouble because the image intensity will change dramatically after several iterations. It will be very troublesome for the training of the network. To deal with these three problems, we think carefully about the existing methods. We find that all of these existing methods share some common things. All of them require the cardioc phase as a minimum unit. That means this k-space points, k-space lines are the minimum unit. We need to do the transform like with this batch and to get the image. But actually the sampled k-space points are at a finer scale. Maybe we can just learn a representation of the k-space from these undersampled points. We borrowed some idea from computer vision field, which is called implicit neural representations. Generally speaking, implicit neural representation is just to learn the coordinates to value mapping. For example, if we want to learn the implicit neural representation of an image, we need to input the coordinates of each pixel into the network, and we make the network to output the RGB value at these specific coordinates, and we use a real RGB value to supervise the training of this network. The philosophy of this method is to learn a continuous representation from sparse and discrete samples. And it has been successfully applied to different modalities, for example, images, shapes, and audios. But how can we apply it into k-space? That's also very simple and intuitive. We also do the data binning and we also do the data sorting and mapping to get the k-space within 1 heartbeat. But we do not do the data binning anymore. We just grab every point from the k-space, sample k-space. For each point, we have their coordinates, their timestamp, their kx, ky, which means their location in the k-space, and also the coil index indicates which coil does this signal comes from. And we put these coordinates into a very simple multi-layer perception network with sign activation functions, and we output the prediction value at this specific point in k-space. And because we rarely sample some values with a sampling trajectory, we can calculate the loss between the sampled value and the predicted value, and we can use this loss to supervise the training of this network. That's the training, and during inference, we just simply generate k-space coordinate grid on Cartesian grid, coordinates on Cartesian grid. For each point on the grid, we have their own coordinate t, kx, ky, and c. And we input every point into the network point-wisely, and we can get the prediction of each point in the k-space also point-wisely. Because these points are already on Cartesian grid, we do not need a non-uniform FFT anymore. We can simply apply inverse Fourier, faster Fourier transform, and coil combination to get the final image. So that's the main diagram of our methods. We first do the data acquisition and mapping and sorting. Instead of doing the data binning, we do the point-wise training of the network. And during the inference, and we just generate coordinates on Cartesian grid and get the prediction on Cartesian grid, and then finally get the image. All of this training are done with the data from this specific scan and with the specific unsampled data. We do not need a large training data set anymore. And also, because we are doing the point-wise training, we do not care about the sampling trajectory, and we also have the created case-based Cartesian grid, and we do not need non-Cartesian, non-uniform FFT anymore, and we do not have the data binning, so we do not have this temporal resolution loss. To make the training of the network more smoothly, we also introduce two tricks. The first one is frequency domain regularization. Generally speaking, we introduce a regularization term to the loss of the network. Here's a regularization term, and F is an image domain denoiser, which can be a convolutional image domain denoiser. And X hat is a predicted image. And if the predicted image is a noisy image, after denoising, we will get a clean image. That means this term will be a large term. And if we already train the network very well, and we will get a clean prediction. And after the denoising, we will still get a clean prediction. So that this term will be very small. And that means by regularization, by introducing this regularization term, we can ensure that the network can produce some clean images. But that's in image domain. How can we apply it into our frequency domain, which is also case-based? We just find out that the convolution in the image domain equals a point-wise product in the case-based. So that the convolution, the denoising with the convolution in in image domain can be written as a production in the case space, but with the representation, the frequency representation of this denoiser in the case space. And the second trick is a high dynamic range loss. The motivation of that is to compensate the large range of the case space values. Because in case space, usually we have a very high value as a case space center, but there are just a few points. But in the high frequency part, which is outside of the case space, we have a large number of points with very, very small values. This imbalanced distribution will corrupt our training. So we just introduce a log transform to our loss and to correct the distribution a little bit. And we can see without the HDR loss, the training only focuses on the high value part, which is at the case-based center, and the image quality is very low. But with the HDR loss, we can train the whole case space very well, and we get the very good detail of the image. We conducted our experiment on 6 healthy volunteers, and each volunteers has 7 short axis slices. And we compared our method with inverse NUFFT and CG sense and L+S. And we evaluate the results with a normalized root mean square error and PSNR and SSRM. Regarding the quantitative results, if we take a look at the reconstruction results from the data from the 4 heartbeat reconstruction, that means we use data from 4 heartbeats to reconstruct the whole image. And our proposed method is way better than the comparison methods. And when we even push the limit even higher, we use the data from only one heartbeat, the reconstruction result is still very good comparison to the other methods. Here's some visual comparison for the 30 frame reconstruction and with the data from 4 heartbeats. And here are the reconstruction with inversing UFFT. We can see the image contains a lot of noise and also striking artifacts. And with our proposed method, we can see the image is much cleaner. And here's a comparison side by side. Our method has much more detail comparison the inversing UFFT. And comparison to CGCS and L+S, our method also has some benefits. For example, has less striking artifacts and much more detail. And when it comes to the reconstruction results from only one heartbeat, we can see the inversing UFFT almost failed to get the shape of the heart, just corrupted with a lot of striking artifacts. But with our method, although the image quality is not very perfect, but we can still keep most of the details of the heart. And here's a side-by-side comparison. And also comparing to CGCS and L+S, our result has much more detail. For example, the the cardiac muscles here. But our method also has some limitations. For example, it usually has a very long reconstruction time. We usually need to spend 30 minutes in our current version to train and reconstruct the network for each scan. And we also observe that the HDR loss is very sensitive to k-space data distribution. And we also find that the model doesn't work well with the Cartesian scheme. It only works very well with the radial sampling. So in summary, we propose a novel k-space point estimation scheme, use a near implicit function for non-Cartesian cardiac MR imaging. And the non-Cartesian we achieved a non-Cartesian reconstruction without NUFFT and conventional grading, and with an arbitrary number of cardiac phases and without data binning. And all of this training is on the specific scan, and it's a single shot reconstruction. No additional training data is needed. And maybe in the near future, it can also be applied to MR fingerprinting and also motion resolved MRI. So that's all my colleagues for this work. They are Hongwei Li and Jiazhen Gashtao, Daniel Ruckert, and Kerstin Hamnick. And thank you very much for listening.